It's my pleasure to introduce our speaker, Professor Subin Pulari, with his talk, When Normality Meets Automata, Dimension, Selection, and Randomization.
Thank you. So thanks for coming. So today in the talk, When Normality Meets Automata, so the talk is about like two broad research programs in finite-state randomness that I was also a part of, and I would like to give you an overview of the kind of questions we deal with in this programs, and maybe also indicate the future directions and some open questions regarding dimension, selection, and randomization. So in the first part of the talk, we will talk about dimension, which is finite-state dimension. So it's a measure of randomness in a real number, and so we'll define this notion, and we'll look into something called the normality dimension thesis, and we will review some recent results and some recent progress that that we had done in the past few years, and then we'll also highlight some future research directions with regards to the normality dimension thesis. In the second part, we talk about selection and randomization. So here we deal with probabilistic automata, and we ask questions like, with respect to selection and randomization, are probabilistic automata any better than deterministic automata? So we'll do this in context of two theorems. One is the Bienvenu theorem for normal numbers, and the other one is the Schnorr and Stimm theorem for normal numbers. And we will extend a result by Lechine and his co-authors from 2024, and we'll prove something called the Bienvenu theorem for probabilistic automata. So we generally will see that probabilistic automata are not really any more powerful than deterministic automata in certain contexts. So we start with the first part, that is dimension. So we have to first at least introduce the finite-state dimension of a real number. So finite-state dimension of a real number is a measure of randomness in a real number, and typically some of you might have already must be familiar with this notion, but for others I will introduce the kind of quantity that we are trying to build. So let's say we have a real number. So we will we will study both real numbers and sequences equivalently, because if you have a real number, you can look at its infinite binary expansion, and that defines a sequence. And if you have a sequence, we can look at the sequence as a real number by considering the real number having that binary expansion. So we will use both these concepts we'll exchange them throughout the talk. So if we have a real number, we want to build a measure of randomness in the real number. So a highly non-random real number, like a periodic real number, a number having periodic expansion, or all zeros real number or all ones real number, will be highly non-random, and it will have finite-state dimension close to 0. And a partially random real number, like a real number in which half of the digits are totally predictable using finite-state automata, will have finite-state dimension roughly half. So I haven't really defined what I mean by random, but we'll give a very precise answer to that in a few minutes. And a totally random real number, which we'll see that they are actually equivalent to something called normal numbers, will have dimension exactly equal to 1. So this is roughly the kind of quantity that we are trying to build. So this was originally defined by Lutz, Lathrop, Lutz, and Majordomo using a concept called finite-state gamblers. We will see finite-state gamblers towards the end of the talk, but for now we'll be using another formulation. And this is a quite robust mathematical notion, because in later years several authors came up with different formulations of finite-state dimension. So there is one in terms of automatic Kolmogorov complexity by Kosaczynski and Chen, and there is one in terms of compression ratio using finite-state compressors by Burke and several others. And the formulation we'll be using today will be the entropy rate characterization of finite-state dimension. using which finite state dimension has this definition. So so I'll begin by actually introducing this definition to you, what it actually means. So this is the entropy rate definition of finite state dimension. So what does it actually mean? So in order to start with it, I will start by defining block entropy, which is the fundamental building block in the definition of finite state dimension. So let's say we have a finite string, something like this, and let's try to calculate the two-length block entropy of the finite string. So for this, we will start by just taking the counts of every two-length substring within this string W. So for example, there are 6 zeros in the above string, and etc. Up to 1, 1. Now, if we divide this by the total number of two-length blocks, we get a probability distribution over the set of all two-length strings, and the two-length block entropy is just the normalized Shannon entropy of the distribution.
So the blocks can overlap?
Yeah, for now, yeah. But we'll later see that, it doesn't really matter.
Okay.
It was proved by Shen and Koziczynski that you can either take overlapping blocks or disjoint blocks. Doesn't really matter. And so so we have this distribution. We calculate the Shannon entropy of the distribution, which is minus p log p, and we normalize so that this quantity is between 0 and 1. And here the normalization factor is 2, because there are like 4 elements in the probability space, so the maximum possible entropy is log of 4. Yeah, so that's the two-length entropy, and similarly we can easily extend this definition to any length L, right? So
I'm sorry, but completely naive question. I'm not from this area.
Yeah.
But why people do like so much this logarithm? Why should you multiply it by this logarithm? What is the reason?
Oh, so like this factor?
So you have this P, Z, W. Okay, this is a very clear, you explain what is this. And you multiply it by logarithm of the same number.
Yeah.
What is the logic? Why do you do this?
So this is, you can view the Shannon entropy as like the average amount of uncertainty involved in the probability distribution.
It's
so for
interpretation as code length. So
Yeah.
if you have a source that has a certain Shannon entropy, you can build a compression algorithm that compresses the object up to this Shannon entropy.
Yes.
And so if you code with bits, you need binary logarithm. If you code in ternary alphabet. So if you have...
I understand that people normalize something if they want to be the sum of something equal 1, something like this. Here also some reason of this type?
Well, the 1/2 make sure you get something between 0 and 1.
And logarithm?
So the 1/2 corresponds to the length of W, which is 2 in this example. The logarithm has to do with the coding interpretation. So expected value of logarithm is expected value of the code length. So if you have 8 objects that are uniformly sampled, you can encode them using 3 bits.
I see.
Yes. So that,
Yeah.
So, so then we normalize so that we get a number between 0 and 1. And for the above distribution, we can even check that it's something like 0.95. And for a general length L, what we do is that we begin by defining the occurrence probabilities. So if we have a longer string W and a shorter string Z, the probability of occurrence of Z within W is obtained simply by counting the number of times Z occurs within W and then dividing it by the total number of Z length blocks. And now if we look at this quantity and we vary Z over every L length string, we get a probability distribution over sigma to the power L. Sigma is a finite alphabet. And now the L length block entropy is just the normalized Shannon entropy of this distribution. So we have this distribution, we take the Shannon entropy, and here the normalization factor is L, because there are 2 to the power L elements in the probability space. Yeah, so that would be the definition of L length block entropy. And coming back to dimension, so we are trying to build a measure of randomness in a real number. So we have a real number x, and so we start by looking into this quantity. So we take the L length block entropy in the first n bits of the real number x. So capital X is the binary expansion of the real number. We take the first n bits and we calculate the L length block entropy. Now this quantity has two variables inside it. One is the block length and the other one is the number of bits we are considering. Right, so n and L. And as n goes to infinity, this quantity need not have a limit. In fact, you can build very simple example of numbers where this quantity does not have a limit, but it will have a limit inferior. So we apply the limit inferior here, and now in this new quantity there is only one variable, which is the block length, and in fact it's a non-trivial argument where you can actually show that this inner quantity has a limit as L goes to infinity. So that was shown by Shen and Kozaczynski. So applying the limit here, finally we have a number between 0 and 1. And we say that we define this to be the finite state dimension of the real number. So we could have instead applied a limit superior here, but that is also quite meaningful. That will define something called the strong dimension of the real number. That's like a dual quantity. But in this talk, we'll be only dealing with the finite state dimension. All of these theorems can equivalently be done in the setting of strong dimension as well.
On the left-hand side, you have small x. On the right-hand side, capital X.
Yeah, so x is just a real number in 0, 1, and we just use capital X to denote the binary expansion.
So this is the same number but origin.
Yes. So this is an infinite sequence of bits. This is a real number, just notation. And if in trivial cases like when X has two different binary expansions, we can choose either of them. We'll fix a convention like choose the one ending with all zeros or something.
So they have entropy 0 anyway.
Yes.
If you have a rational number because of repeated expansion.
Yes. So the definition doesn't get affected by the choice. You can choose it.
So the convention logarithm of 0 is 0 times log 0 is 0, to be precise in the Shannon definition.
Good news.
Yeah.
Yeah, so let us try to understand this definition by looking at some examples. So what we wanted was a measure of randomness which has this kind of properties. So for example, you can easily verify that if you have a periodic sequence or an all-zero sequence, you can easily verify using a direct calculation that such sequences have finite state dimension equal to 0. Now we come to the partially random and random cases. So we'll start by addressing the random case first, because that's the most interesting concept for us in this talk, that is normality. So through a line of work starting from Schnorr and Stimm from 1972 all the way up to Burkitt, Koch and Vinod Chandran, it was established that a number has finite state dimension equal to 1 exactly when the number is something called a normal number, which is a well-defined, well-studied notion in mathematics, and we'll look into the properties of what normality is after this. So the numbers having maximum randomness with respect to finite state dimension are exactly the normal numbers. So what is a normal number? It was originally defined by Borel in 1909, and in base 2, we'll simply a number is base 2 normal. If we consider any binary block of length k, w, it appears with the limiting frequency 2 to the power minus k in the expansion of the real number. So more precisely, if we have a real number x and we consider any string z of length l, and we look at the occurrence probabilities of z within the first 10 bits of x, this converges to the uniform distribution 1 over 2 to the power n. So intuitively, any block of length L is equally likely to occur within the expansion of the number, in the limit. So, yeah.
There were two famous Borel, Armand Borel and Émile Borel.
Emile Borel.
Émile Borel,
Yes.
who was Prime Minister of France. Okay.
All right, so I suppose the definition is clear, so yeah. So normality is randomness with respect to frequencies of occurrences, right? So so if you want, let's look at some examples. So there are many interesting examples of normal numbers. So the first number which was explicitly shown to be normal was the Chambernau number, and this is obtained using a simple rule. We start with, let's say, the one-length binary strings, which is just 0 and 1. We attach them together, then we go for the two-length binary strings. So there are 0, 0, 0, 1, 1, 0, and 1, 1, and similarly we keep on attaching like 3-length, 4-length, 5-length, etc., and we get an infinite sequence. So Chambernau showed that this number, for example, is normal in base 2. Chambernau did it for base 10, but the same proof can be adapted easily to base 2. So this is a very simple number which is normal. Then there are other interesting theorems as well. For example, Copeland and Erdos showed that if you take the set of prime numbers and you concatenate the binary expansions of the prime numbers, like B2, B3, B5, B7, etc., this infinite sequence is a normal number. Now for non-normal numbers, of course, you can consider any periodic sequence, because in a sequence like this, obviously many blocks doesn't even occur, right? So they're definitely not normal. And there are also other kind of complicated sequences, well-studied sequences like two-more sequence, for example, which is obtained by certain complementation rules. And these kind of sequences are also known to be non-normal. For example, in the two-more sequence, something like 0, 0, 0 and 1, 1, 1 will never occur. So, yeah, so those are some examples of normal numbers and non-normal numbers. So, and very important open question in mathematics is to actually show whether the natural constants like root 2 or pi and e are normal numbers or not. So there's a lot of experimental evidence suggesting that all these numbers are actually normal. But no one has yet managed to give a proof that these are normal numbers. And if you want to produce a normal number, you can simply do it by a random coin experiment, because if you toss a fair coin independently forever and you interpret the heads as a 1 and the tails as a 0, with probability 1, you will get a normal number. And this is just an informal way to state the following theorem by Lebesgue, which says that almost every real number in the unit interval is normal. So a probability 1 set of real numbers in 0, 1 are normal. So there's an abundant supply of normal numbers in the unit interval. So coming back to dimension, we know that if number has finite-state dimension equal to 1, if and only if it's a normal number. And from the entropy rate characterization, at least proving one of the directions is quite trivial. So if it's normal, it's very easy to show that it's dimension equal to 1, right? And showing the other direction also is not so difficult, but it involves a bit more calculations. So these are numbers having maximum dimension. So a class of numbers which has the minimum possible dimension would be, let's say, a rational number, because every rational number has a eventually periodic expansion in any base. So again, using a direct calculation of entropies, you can show that every rational number has finite-state dimension equal to 0. So the picture is the following. So we have the spectrum of dimensions, and on the one end of the spectrum we have normal numbers, which are exactly the numbers which has finite-state dimension 1. On the other end of the spectrum, an example of a class of numbers having dimension 0 would be rational numbers. But there are also, you can easily construct irrational numbers which has dimension 0. And for intermediate dimensions, there are simple tricks to construct numbers. For example, if you want like a dimension half number, what we can do is that we can start with a normal number and just dilute it by inserting a 0 in every alternate position. So you can again do a hands-on calculation involving entropy rates and show that this number has dimension half. And if you want like a 1/3 dimension, we can insert 2 zeros. And similarly, for any rational number, we can easily dilute a normal number and obtain a number having that dimension.
May I ask you, and in this first line, when you have 1/2,
Yes.
if you will replace 0, 0, 0 by some periodic sequence,
Yeah. Yeah, as long as it's like easily predictable by an automata, that's totally fine.
so it will still be 1/2.
Yes. For example, 0, 1, 0, 1 is totally fine. All right. So yeah, so for intermediate dimensions, we have diluted sequences. So yeah, again, if you want irrational dimension, you can do some approximation kind of construction and also construct numbers having dimension pi, like 1 over pi or whatever you like. So in the light of all this, like we can view normality as a special case of dimension. And so this is the point at which the normality dimension thesis comes up, but it says something much broader than this. So in 2022 in CCR, Lutz proposed the normality dimension thesis, which postulates that every theorem concerning Borel normality is the dimension 1 special case of a more general theorem concerning finite-state dimension. So what does it mean? So like, so we'll see some examples of validations of this thesis. So instead of just saying that normality is a special case of dimension, it kind of postulates that any theorem concerning Borel normality can be expressed as a dimension 1 special case of a more general theorem concerning dimension.
What is CCR?
Oh, it's computability, complexity, and randomness. It's a workshop.
Ah, this is some conference. Some
Yes, yeah.
And this statement is precise, so it's possible to say what is more general theorem.
No, this is just a thesis in a sense. It's not a very. We can try to make it precise, but this is like exactly how Lutz stated it in the conference. Yeah. As this is in this form, it's not very precise, of course. But Lutz came up with this postulate in the light of several results, some of which I would like to show you. So, for example, one nice example is the one of these classical results by Wall, which says that if x is a normal number, then if you add a rational number or multiply a rational number with this normal number, then it still remains normal. So addition and multiplication with rationals does not affect normality. A dimension version of this was given in 2006 by Lutz and Nandakumar, who showed that for any real number x, if you take a non-zero rational q, then the finite-state dimension of x plus q and x times q is equal to the finite-state dimension of x. So why is this theorem a generalization of this? That's because if you substitute the case when finite-state dimension of x is equal to 1, then you immediately get this one, right? Because that implies that x plus q and x times q has dimension 1, and so that exactly says that they're normal. So this is another result. This is slightly different, but then again it's a vast generalization into arbitrary dimension. So let's consider this another classical result by Copeland and Erdős, who showed that the real number found by concatenating all prime numbers is normal. So there was a very elegant paper by Gu, Lutz, and Moser in 2007 in which they generalized this to a vast set of numbers. So here we consider any subset of natural numbers, so A can be the set of prime numbers in this case. Then CE of A just denotes a number that we obtain by concatenating the binary expansion of every number in the subset A. So in case A is the prime number, it's exactly this number. And they showed that the finite-state dimension of this number is greater than or equal to something called the zeta dimension of the set A. So this is a well-known notion from number theory, which is like a kind of a density of subsets of natural numbers. And how is this theorem a special case of this? That's because if we consider the set of prime numbers as a consequence of the prime number theorem, it can be shown that the set of prime numbers has zeta dimension 1. And due to that reason, if you take A to be the set of prime numbers, then the left-hand side will be equal to 1, which is what is being asserted in coherent.
What is this round bracket? What does it mean?
Just the binary expansion of 2 and binary expansion of 3, binary expansion of 5. Yeah, so that is, let's say, another instance. There's maybe, this is another one, which, this is again a classical result by Pillay. So this is what Bruno was asking at the start. So Pillay had shown in 1940 that a real number is, normality is invariant whether we count the occurrence of strings in a sliding fashion or we take the disjoint counts. So a number is normal whether we consider, like defining normality using sliding counts or disjoint counts gives you the same notion of normality. And this was again generalized by Shen and Kozaczynski, who showed that whether it doesn't matter however we define dimension, whether we define dimension using sliding counts or disjoint counts, the dimensions are the same. So again, this theorem is a special case of this, when the dimensions are equal. So in the light of all this, Lutz proposed the normality dimension thesis, and in the first part of the talk, I would just like to talk to you about, so these are a few examples that we showed. So there were a few other examples, a few other instances of the validation of the normality dimension thesis. So that's what I would like to summarize in the first part of the talk and just maybe propose a few future directions. So is it like clear, like what the normality, are there any questions at this point?
How do you transform Borel's theorem that almost all numbers are normal?
Oh, almost all real numbers are normal. Well, the set of numbers having any dimension less than 1 are in a measure 0 set. So, I don't know if that theorem would have an interesting generalization, but
I also don't.
Yeah.
The set of real numbers with positive dimension is dense. Because normal means dimension 1. No?
Yeah, that I'm not pretty sure about. Like, yeah, that's interesting. Yeah. Maybe there's some finite tree formulation of the measure property that can be added. Okay, so the results I would like to talk about are like, there are 3 results. One is concerning the real numbers equally compressible in every base, which generalizes something called absolute normality. Then there is a recent, this is a very recent result with concerning finite-state dimension and automatic subsequences, and probably I won't go into this because that would take a lot more time. So, so I have till 7:30.
Yes.
Okay. Yeah.
Maybe 10 minutes of questions.
Yes.
Yes.
Okay. Yeah. All right. So maybe I'll talk about the first result in the list, which is real numbers equally compressible in every base. This was a joint work with Subin and Nandakumar, and so in order to introduce this, I have to first talk about absolute normality. So the definition of a normal number can be easily generalized to any base by saying that, by defining that a number is normally in base B, if for any length L and any string Z of length L, the occurrence probabilities are converging to 1 over B to the power n instead of 1 over 2 to the power n. And having defined this, we can define absolute normality, and we say that a number is absolutely normal if it is normal in every base b for positive integer base b. And again, from Lebesgue's theorem, we can immediately get that almost every real number is absolutely normal. And so, just a picture, so this is, okay. So now, look from the connection between dimension and normality, we can extend all this all the definition of dimension and everything to arbitrary base, and we can get the following connection that a number is absolutely normal if and only if its finite state dimension in base b is equal to 1 for every base b. And on the other end of the spectrum, we can look into rational numbers. Like rational numbers have eventually periodic expansion in every base. So it's very easy to show that any rational number has finite state dimension equal to 0 in every base b. So in a picture, so rational numbers and absolutely normal numbers are absolutely dimension numbers because their dimension doesn't really depend on the choice of base. So here is a pictorial representation. So if we have the set, if you look at all the bases, at the lower end we have rational numbers because they have dimension equal to 0 in every base. At the top we have absolutely normal numbers which have dimension equal to 1 in every base. And we already know that if you want to construct like a 7/8 dimension number in base 2, that we can do by diluting a normal number, for example. But the issue is that we have absolutely no idea about the dimension of this number in base 3. There are no known techniques of calculating. So let's say we diluted a normal number to get a 7/8 dimension number in base 2. It's not really known whether this number is normal in base 3. Even something as simple as the Chambernois number, if you write it down in base 2, it's not really known yet whether that is normal in base 3. So translating from base 2 to between bases is still quite a difficult question. And similarly, if for any pairing of dimension and base, we can construct numbers having those particular dimensions in those particular bases. But then we really don't know about their dimensions in the other bases.
So you say it's not known whether Chamberlain number from base 2 is
Yes.
normal in base 3.
Yes.
But it cannot be so difficult to...
Oh yeah, but maybe you can, I think experimentally it is probably normal, but then proving it is, there's no known proof of whether that is normal in base 3.
Okay.
Yeah.
We should ask a student.
Like there are other kind of series where you can verify that it's normal in base 2 and 3 simultaneously. But for the Chambernois sequence, there is no known proof.
Okay.
Yeah. Because the moment you convert to another base and you try to look at the digits, you have all these carries coming from long blocks of digits, and it gets really messy. And so it's not a very. Probably someone will develop a technique later, but as of now, there is no real tool we can use to do that efficiently. So this is the situation that we have right now. And so Lutz and Mayordomo had proposed a question which asked whether there exists a number of the following form. Like, does there exist a number whose dimension is the same in every base, but it's strictly between 0 and 1? So, and this is the question that we answered in a joint work with Nandakumar. And so this is the precise formulation of the problem. Does there exist an R strictly between 0 and 1 and a number x whose dimension in every base b is equal to R? And in our work, we actually showed something more powerful than this. We showed that given any sequence of rational numbers, QB, such that we are trying to construct a number whose dimension in base b is QB, as long as this sequence represents certain, respects certain natural equivalences, there exists a number x whose dimension in base b is equal to QB. So what do I mean by natural equivalence? The reason is that we have the following, that certain bases are equivalent. For example, base 2 and base 4. Because if we consider a real number, its base 2 dimension will always be equal to its base 4 dimension. This can be easily verified by direct calculation. So in general, we have a definition of equivalence between bases. We say that R and S, two different bases, are equivalent if there exists two powers like R to the power n and S to the power n, which are the same. So like 4 and 8 are equivalent bases, or 2 and 16 are, using this equivalence we can get an equivalence class. Equivalence, we have an equivalence relation when we can divide the set of bases into various equivalence classes. And the fact is that if two bases are equivalent, then for any real number x, their finite state dimensions are always equal in those bases. So there can never exist a number whose base 2 dimension is not equal to its base 4 dimension. So coming back to the theorem says that as long as the sequence of rational dimensions QB respects this necessary equivalence condition, there is a real number x such that the dimension of x in base B is QB. And why does this solve the original question? So with this tool, what we can do is that, let's say we are given a set of requirements, like we are being told that we have to construct a number whose base 2 dimension is 7 over 8, whose base 3 dimension is half, whose base 5 dimension is 1 over 4, etc., etc. Then the theorem tells us that there is a number which satisfies all these conditions. And in order to get an absolutely normal number, all we have to do is to maybe set all of them equal to half. So now that's an absolutely dimension number whose dimension is strictly reducible. So yeah.
Sorry,
Yeah.
can you please show the previous slide with your result
Yes.
for a second?
Yes, sure.
Just to read.
Yes, sure.
Thank you, thank you.
But 1 is included in the interval. So if it's the
Are we talking about this one?
yes, so you
So this
include
is-
1.
Yeah, we can enforce normality in one of the bases, yes.
But if I remember correctly, then
Yeah.
the number is normal and in this base, and
Yes.
then it's normal in every base.
Oh, no. Those are only the sequence numbers which are absolutely normal. So we can construct numbers which is normal in base 2 but not normal in base 3.
So the sequence of, okay, I'm sorry.
Yeah. So this theorem allows us to, let's say, construct a number which is normal in base 2 but has dimension like 1/4 in base 3, for example.
Okay, I misremembered something. Yeah.
Yeah. So all I said was that if we define, when we look at absolutely dimension numbers, they're defined to be the numbers having, which are normal in every base. But such a number is definitely not absolutely normal.
Yeah.
Yeah. Yeah. Is that clear?
Yes.
So yeah, so I probably have a little bit of time to talk about the proof, but again, so yeah, maybe I'll quickly go over it. So just to give a flavor of how this kind of a number is constructed, so the proof actually stems from an important connection between normality and exponential sums, which is given by something called the Weil criterion for normality. So Weil in 1916 gave a very nice way to characterize normality in terms of exponential sums. So Weil proved that a number is normal if and only for every non-zero integer k. This sequence of Weil averages, as they are called, converges to 0. So what exactly is the sequence? So
This is an old Weil, German Weil.
Hermann Weil. Yes. So here what we do is that we start with the number x. We keep on multiplying the number with powers of 2. So in each successive multiplication, we are shifting the binary expansion of the number one position to the left. Then we take the classical exponential functions from Fourier analysis, the e raised to 2 pi I k y, which maps the unit interval into the unit circle in the complex plane. So here the number k kind of determines the number of windings that the mapping does around the unit circle. And now we apply the exponential function to the sequence, to the sequence above, and we get a sequence of complex numbers. And then we take the sum of these complex numbers, and we take the average, and we study this average. And the Weil criterion for normality tells us that a number is normal if and only if for every non-zero integer k, this sequence of Weil averages are converging to 0. So if it's normal, then we have convergence to 0, and if you verify that the convergence happens to 0 for every k, then we can be sure that the number we started with is a normal. And the reason why this helps us in the construction, so from the connection between normality and dimension, we immediately get that a number has dimension equal to 1 if and only if the Weil averages are all converging to 0. So at this point, from this theorem, there's just a fact I would like to stress on. So we have the phenomena of having low exponential averages, or exponential averages converging to 0. So from the Weil criterion, we know that this kind of corresponds to having uniform distribution of digits in a number, because that's exactly what Weil criterion gives us. And we already know from the entropy characterization of finite-state dimension that this is also equivalent to having an entropy rate close to 1. So these are like, all these three things are roughly characterizing the same phenomenon. So one is a number theoretic way of studying it, the second one is a combinatorial way of studying it, the last one is like an information theoretic way of studying it. So all of these corresponds to normality or uniform distribution. So yeah, I won't have time to go into the details of the construction, but basically what we do, so just to give you a flavor of how absolutely dimension number is constructed. For example, let's take a toy example. Let's try to construct a number whose dimension in base 2 is q2 and dimension in base 3 is q3. So q2 and q3 are some real numbers between 0 and 1. So let's say the picture is something like this. We have 0 to 1 and there's q2 and q3. And in the proof, what we do is that the whole proof is trying to create some controlled oscillation of the Bloch entropies. And the oscillations are created in the following way. So let's say, let the green circle represent the base 2 entropy, let the blue circle represent the base 3 entropy. So in the proof proceeds in a stage-wise manner, and in every odd stage, so this is just to recall the definition of finite-state dimension, and just to notice that we have a limit inferior in it. So coming back to the construction, in an odd stage, what we do is that we bring down the base 2 entropy of the real number close to q2 and take it back up again. And the way we do it is that while we are doing this, we will minimize the Weil averages in base 3. So we create an oscillation in the base 2 entropy while we minimize the Weil averages in base 3. And we already know that having a low Weil average corresponds to uniform distribution. So that's the reason why the base 3 entropy remains close to 1. And in an even stage, we do the opposite thing. We fix digits in base 3 and bring down the entropy to q3 and then take it back up again. While this is happening, we will ensure that the Weil averages in base 2 are low. So since Weil averages in base 2 are low, that means the digits are uniformly distributed in base 2. And the entropy rate is somewhat stable around it. And in successive stages, such a number, we keep on doing this again and again. We bring down the base 2 entropy, and in the next stage, we go ahead and bring down the base 2 entropy, and keeps on going like this. So the stages create this kind of oscillations in the base 2 entropy and the base 3 entropy. And we stick all of them together like this. And since the finite state dimension is defined using limit inferior, it's directly verifiable that such a number has dimension equal to Q2 in base 2 and Q3 in base 3.
So how do you bring them together?
Yes.
You alternate the blocks?
Yes, in alternate blocks. And the way in which we bring down the entropies while stabilizing the Weyl averages in the other base. So those were, so there's a long line of work starting from a construction of absolutely dimensional numbers by Wolfgang Schmidt in the early 40s, which gives some number theoretic tools in which we can fix digits and simultaneously control Weyl averages in another base. So we adapted to the setting of finite state dimension and use some entropic calculations to control this whole thing. So we keep on alternating between bases. In one base, when we are controlling the entropy, in every other base, the Weyl averages are small. Yeah. So it's, yeah.
So it's not just take a part of, so you have two numbers, and
yeah.
then you take blocks from both parts, but you have to apply corrections.
Are you concerned like whether future stages will?
Yeah. Okay, I just ask a question. Maybe I'm wasting everyone's time, but so yeah, I understand you can construct two numbers.
Yes.
And then your construction is that you combine these two numbers in one number.
So we are only constructing one number.
Okay.
We'll construct a number up to a certain precision. Then beyond that, while constructing the next stage, we will fix digits in another base.
Okay.
So we are really only constructing one number here.
Yeah.
But we keep on increasing the precision as the stages go on. Yeah. So that was the real numbers equally compressive in early base. So this is again a validation of the normality dimension thesis because it vastly generalizes the fact of existence of absolutely normal numbers to the existence of numbers having any kind of dimension you want in the sequence of bases. Right? So yeah. So that was the result, and maybe I'll talk about this one also and probably skip the last one. So the next one is concerning finite state dimension and automatic subsequences. So this is my most recent work with Bienvenu and Hugo Gimbert, and this concerns something called the Agafinov theorem for normal numbers. So Agafinov in 1966 gave another characterization of normality. It's in a way a characterization, but it's also an interesting fact about normality, which says that a real number is normal if and only if any subsequence that is selected by a finite state dimension from the real number is normal. So I'll explain what this means. And in order to do that, I'll have to first talk about automatic selectors. So an automatic selector is just a finite state automata that is selecting digits from an infinite sequence. So the idea is that the finite state automaton reads an infinite sequence. Some of its states are marked as selecting states, and whenever it reaches a selecting state, it will select the next input symbol. And so using this, using a simple inductive definition, we can define the subsequence that is selected by the selector. So how does this happen? So let's say locally a selector would look like this. So from every state there are two transitions, 0 and 1, and some of the states are marked as selecting states. And we'll denote the subsequence that is selected by the selector from the sequence X as select S, X. So for a simple example, let's consider this selector. So this symbol selector, which starts from the state A and keeps on alternating between A and B. Let's say we take such a sequence X, we can easily verify that this would select all the digits at even positions. Like whenever it reaches state B, it will select the next input symbol. Right? So this is a simple example of an automatic selector, but in general, automatic selector can be much more complicated than this. It can be a much more structured finite state automata with different patterns of selectors, selecting and non-selecting states. And so this is how I would like to introduce the Agafinov theorem. So suppose we have a sequence X, an infinite sequence X. Here is an intuition about what this is saying. So let's say we are listing all the automatic selectors in a list. So there are only countably many automatic selectors, so we can do this. Now on the other part of the table, we are recording the behavior of the selected sequence. So the selected sequence can have three different behaviors. Either it's a finite sequence. If it's not a finite sequence, it's an infinite sequence which can be normal or non-normal, right? So we just keep on marking the behavior on the right. And the Bienvenu theorem tells you that a number is normal, a sequence is normal if this table will only have two possible options. Either it's finite or normal. So more precisely, X is normal if and only if for every automatic selector S, select SIX is either finite or normal. So the non-trivial part of the theorem is in showing that from a normal sequence, a finite state automata can never select a non-normal sequence. So in a way, it tells you that finite state automata cannot really detect any kind of biases given a normal sequence. The only thing it can do is keep on producing normal sequence from normal sequences. Is that clear? Yeah. So more precisely, this would be the statement of the Bienvenu theorem. So the following are equivalent, that a sequence is normal if and only if for every automatic selector S, the selected sequence is either finite or normal. The finite is trivial. I mean, maybe a selector doesn't select anything, so then it's an empty sequence, right? So there are many trivial cases, but otherwise it can only produce normal sequences. There is absolutely no way that a finite state automata can detect any kind of non-normality within a normal sequence. And that is so this is yet another rephrasing of the theorem. So as I told, the non-trivial part is X is normal implies no automatic selector selects a non-normal subsequence. And so when we come to finite state dimension and so this is a theorem concerning normality, and we can try asking questions like, what is there a generalization of this for arbitrary finite state dimension? And when we try to look into generalizations, the things are somewhat difficult because of the fact that there are symbol sequences, let's say the above sequence, whose dimension is half, from which this symbol selector can select a normal sequence, while the complement selector can select a sequence of all zeros. So from a half dimension sequence, you have the output can be a normal, like a totally random sequence, or even an extremely non-random sequence. So directly there is no such generalization. But in a recent work, what we showed is that, so this would be the question: is there a more general theorem relating finite set dimension of X and the finite set dimension of the selected sequence, such that the Bienvenu theorem for normal numbers is a dimension 1 special case? Because in that case, it would confirm the normality dimension thesis for the Bienvenu theorem. So in a recent work with Bienvenu and Gimbert, we had the following idea of looking into, so there's an important connection between the theory of Markov chains and the theory of normality. So maybe I won't have time to get into the precise statements. So we showed that by looking at so if we have a selector, we can look into something called the induced Markov chain of the selector. And then by looking at the stationary probabilities of this Markov chain, and we weight the selected subsequence and the rejected subsequence, there is some kind of preservation. So here is just a formal statement. So we have a selector and we have an underlying Markov chain. So we showed that the dimension of the selected sequence and the dimension of the rejected sequence, when we weight using the stationary probabilities of selection and rejection, it will kind of preserve the normality up to a small epsilon error. So this is somewhat complicated, but since setting it up would take some time, this probably deserves its own talk, so I will not go into details. But we can show that, so it's actually quite trivial to show that the original Lagrange theorem will easily fall out of this inequality. And that's because if you have dimension of x equal to 1, since we have a convex combination on the left, the only possibility is that both of these dimensions should be equal to 1. So that will tell us that the dimension of the selected sequence is equal to 1, which is what Lagrange theorem says.
What is the nature of this lambda s?
Lambda s?
What is the nature of this constant?
Lambda. Yeah, lambda is between 0 and 1. So it is the total stationary probability of all selecting states for the underlying Markov chain of a selector. Yeah, so that's all. So maybe with that, I'll go to the conclusion of the first one. So I won't have time. So the Weil criterion for normality that so today this also has a generalization to arbitrary finite dimension, but I will skip that part.
So the most interesting part. No?
Yeah?
Probably it's the most interesting part.
So probably I'll do it some other time. And
At least how it looks like.
oh yeah, so it looks like, so I had a picture, I don't know if I can explain it like this. So for an arbitrary real number, which is not guaranteed to be normal, so there is a precise relationship between the Weil averages and the dimension of the sequence. So just a pictorial representation, like what we do is that if we start with an x, we can look into the subsequence limits of the Weil averages of the sequence, and then we can calculate something called the Renyi dimension, which is like a fractal measure of these limit probabilities, and we can show that the finite state dimension of the real number is the infimum of all these Renyi dimensions. So starting with the real number, by studying the Weil averages, there's a way of characterizing finite state dimension.
What is mu?
Which mu? Like?
mu1, mu2.
Oh yeah, so if we look at the Weil averages, and we look at all the subsequence limits, all the limiting points of the Weil averages, we can extract a unique probability measure from every limiting point. So a mu would be such a limiting measure. So we start with an x, we go to these limiting measures, we calculate the Renyi dimension of these measures, then the finite state dimension is the infimum of all the Renyi dimensions. Just a pictorial representation. So. But for now, I'll skip this. Yeah, it's an interesting thing, and you can show that the Weil criterion for normality is a simple special case of whatever I showed before. So yeah. So towards the conclusions and future directions in normality dimension thesis. So well, so for me, like more than verifying the normality dimension thesis for different theorems, the more interesting aspect is that when we try to generalize some of these theorems, we actually require quite a new set of tools in order to handle arbitrary dimensions. So when we address like further verification, maybe an interesting theorem that I would like to see solved, and I think many other people working in the same area like to see generalized for arbitrary dimension, would be the following theorem by Davenport and Erdos, who showed that, so this is the classical theorem by Davenport and Erdos, who showed that if you have a polynomial p such that for every n, Pn evaluates to an integer, then the following real number, which is obtained by concatenating the evaluations of the polynomial on 1, 2, 3, etc., is a normal number. And one question is there any way we can generalize this theorem into a statement concerning arbitrary finite state dimensions? There was a very recent paper, like couple of months ago, which kind of verified this for linear polynomials, and they showed that they had some partial results showing that it's quite difficult for quadratic polynomials. But beyond that, we have no idea whether is there a nice generalization of this theorem for arbitrary dimensions. And another interesting direction would be to check if the normality dimension thesis is valid for alternate forms of normality in other representation systems like continued fractional representation or irrational base representations. So, for example, when we look into continued fractional representation of a real number, there are like very strong reasons to believe that the normality dimension thesis is possibly false for these kind of representation systems. So there's this interesting theorem by Van der Heij who showed that. So we know that from the Dichotomy theorem, if we choose an automatic subsequence from a normal number, it's always going to be normal. So Van der Heij had a similar result, which kind of tells you that if you have a continued fraction normal number, whatever sequence you choose from it is going to be normal. It doesn't even say that there exists an automatic sequence which is not normal. It says that every automatic subsequence you choose is going to be normal. So it's quite possible that in other representation systems, analogues of normality dimension thesis are actually false. But then, yeah, though that's another question that's probably interesting. And I think it's also valuable to look into the normality dimension thesis as a meta theorem in logic, because right now, as we were discussing at the start, the thesis itself is quite vague. It's not quite precise, right? So probably it's interesting to properly set this in a formal system. So maybe we can fix a precise formal language where we can express properties like normality, automatic selection, or gambling, or whatever we would like to express. And then if we constrain the set of theorems into a certain allowed set of statements in that language, and we have some way to express the property of being normal or a number having an arbitrary finite state dimension, we can ask whether in this constrained logical setting, is every theorem concerning normal numbers, normal sequences, a dimension one special case of theorems concerning arbitrary dimension. So, and I think probably it is going to be false. There might be, under suitable restrictions, probably such a statement is not true. But yeah, that's it's not very clear. So it's like, should we have like 10 minutes for questions or?
You have 5 more minutes for talk and then questions.
Oh yeah. So even if I start, I don't think I'll finish the last part. So probably this is the probably a nice spot to end.
Okay. So let's take the speaker. There were a lot of questions during the talk, but maybe there are still.
Is it possible to connect this finite-state dimension with Hausdorff dimension? For example, you can take a set of real numbers with some fixed Hausdorff dimension between 0 and 1. Is it possible to say that almost all numbers in this set with respect to Hausdorff measure will have the same finite-state dimension?
So we are considering numbers having, we are considering any set having Hausdorff dimension strictly less than 1? Well, if such a set has like a modulo of random numbers or something like that inside it, the dimension of the numbers can be 1 or...
I'm talking about almost all numbers. You can have a special number, but...
Yes, okay. With respect to a Hausdorff measure.
Yes, with respect to Hausdorff measure.
And it's the answer to your question, how to,
It could be an answer.
Yeah. That's nice.
Because for continued fraction, we can construct a set of numbers with Hausdorff measure between 0 and 1 using continued fraction with bounded partial quotients. And using this way, it's a possible way to connect continued fractions with these numbers of prescribed finite state dimension.
Yeah. Yeah, I'm not sure about that.
Yeah, it's likely to work because for entropy, like on finite strings, in every set, most strings have entropy close to the log cardinality.
Yeah.
Sorry, what I'm saying.
That's
Yeah,
for
yeah.
distributions.
Yeah. I mean the coding lengths. Most of the strings have coding lengths close to the entropy, and coding lengths close to the log cardinality. Yeah. So this indeed.
So is the idea about that if a continuous fraction is simply coded, then maybe its entropy is also small and it will be normal in it will be normal in or have the dimension 1 this connection.
No. If we have, for example, if we consider continuous fractions with bounded partial quotients, then this set has Hausdorff dimension between 0 and 1. So we can try to connect this Hausdorff dimension with this finite state dimension. Probably they are the same. So this is the way to connect continuous fractions with this finite dimension. Finite set dimensions.
So originally, like Lutz introduced constructive dimension, which is like the version of finite state dimension using Turing machines, let's say. So that was introduced as an effectivization of Hausdorff dimension. So I suppose that probably the better question is to see if these kind of sets have constructive dimension strictly between 0 and 1.
There is a formula for a symplectic formula for Hausdorff dimension of such sets.
Okay.
Defined in terms of continuous fractions.
Okay, I see. So this is the set of all numbers whose continuous fraction dimensions only have a limited set of digits, or
Yes.
yes, okay. Yeah.
And certainly in such a survey talk, it's difficult to appreciate how difficult is technique behind this.
Yeah.
So now we need problems for our first or second year students who are very talented, who are winners of Olympiads, but who certainly don't have technical background.
Yeah.
So are some open problems here are approachable for first or second year bachelor students?
Regarding the dimension thesis, like
On this subject.
yeah, like there are a few other normality theorems which I believe will be easily solvable using without too much techniques. But for example, this one is a so this theorem, this question I proposed, is a very interesting question, and I don't think we would require too much other than basic number theory in order to approach it. So there have already been some works in which people try some number theoretic, information theoretic techniques to prove generalize this to arbitrary dimensions. Yeah, and there are a few other theorems, like there was a theorem involving the irrationality coefficient of a real number that is that we were discussing at some point, that is probably solvable using without too much difficulty. But yeah. So there was some progress in this question in the last year using very elementary techniques.
Any other questions? Maybe I have one question. So,
Yeah.
maybe the existence of the normality dimension thesis means that it's quite easy to reformulate the problem about normality in problem about dimension.
Yes.
But is it true? And there are a lot of works from the date when the thesis was postulated for this moment, or is it not so?
So is it?
It's I think it's not easy to see how to reformulate some questions about normality into the dimension.
Yes, it's even getting the right statement is sometimes quite difficult. So,
Okay.
for example, this theorem, I really don't know what would be the right way to try to generalize this. So, yeah, so are you is the question more like, will it be easier to do it for generalize and do it for dimensions, or? So till now, all the questions we have seen and the solutions that are already published, they are all quite difficult when you generalize to finite-state dimension. While in the case of normality, we have something like a trivial way to do these things. But it becomes a really non-trivial once you push it to.
There is no instruction to how to generalize the question to the dimension, yes?
There's no prescribed method or something, but
Okay. Okay. Thank you, thank you.
Thank you.
Any other questions? So let's thank Professor Pulari again.